Good morning. It's March 27th, and this will be the first of 3 lessons that you will have for week 8. Okay. If you go into Canvas, you will see um, our weekly agenda posted on the syllabus or the homepage. Please continue to email me if you have any questions. If you can, send me an email straight from my stat lab, and we can go over the homework problem together. Or just in general, if you need to talk about the course, you can email me so that we can set up a Zoom conference. Okay. As I record more videos, I will create the links. I will put the links in here. I know the 3 lessons that we will have are Intro to Normal Distribution, Finding Probability Using Normal Distribution, and the last one is going to be really Chapter 7, but we will be able to finish Chapter 6 because the only thing that we have left is normal distribution. We will be able to start Chapter 7 today, and we'll be able to finish Chapter 7 next week. And that's all Exam 2 covers. So we'll also talk about Exam 2 next week. Okay. All right, week 8 assignments. I'm just going to keep it short. We have 3 assignments, no data assignments, just my stat lab homework, part 1, 2, and 3. All due next Thursday on April 2nd. And like I said, we have 3 lessons. After each lesson, you should be able to try, after this video, you should be able to try part 1. After the second, you should be able to try part 2. But for attendance, because I still need to keep an attendance in this class, and what I'm going to do is, instead of creating a separate Google form quiz or Canvas quiz, I'm just going to use I'm gonna see if you do at least 2 out of 3 of these My Stat Lab homework. I will mark you present for week 8. Okay, because attendance grade is still 5% of our class. I kept that part the same, but remember, My Stat Lab online homework worth a little more now. So if you're not getting these homeworks done, please remember to, because they're all open for you. You can still do them late. You're just gonna get a little late penalty, but they're always open. So make sure to make them up if you got behind last week. And like I said, we'll talk about Exam 2 next week. Okay. Alrighty, let's take a look. I'm gonna go ahead and go into modules. And this is what you probably see right now. Or if you came in later in the week next week, you'll probably see all of them. But I'm gonna make sure to record everything, and I will post all of them under week 8 so that you have 3 separate lessons for week 8 from March 27th to April 2nd. Okay. All right. Oh, before I go there, let me show you what I posted too. I got an email from a student last week saying that they would like to have a blank copy of the note. So I'm going to start posting them on Canvas too. So this is it. I'm about to go over this note with you. Intro to Normal Distribution note is 7 pages, a PDF. If you want to print it out, we can go over I'm going to go over the slides, and they will just, you'll be able to fill these out, okay? All right. Let me open up the Intro to Normal Distribution Google Slides. All right. In this lesson, I'm going to talk about just some of the basic normal distribution properties, talk about standard normal distribution, and using a table method to calculate some probabilities. But I'm not going to do any stat crunch. I'm not going to use any technology in this. So this may take a little bit longer because we're going to do this the old-fashioned way. And a lot of the basic properties and things that we should talk about before we get to all that calculating part. So this is part 1, probabilities for bell-shaped distribution, also called normal distribution. Okay, so we only have one learning objective in this lesson, and that is to use normal distribution to calculate probabilities. And in this video, we will use the table method. Okay, table method. All right. Last week, we talked about binomial distribution, And binomial distribution is actually a discrete random variable. It's a distribution of discrete random variable. Today, we're working with a continuous random variable, which has an infinite number of possible values. It's continuous, like a measurement, that can be represented by an interval on a number line. So, because we talked about this continuous and discrete before. For continuous random variable, a value can take a number can be any value in between two numbers. Like for example, right here, suppose somebody asks you, "Hey, how many hours do you spend studying in a day?" Your answer can be about 3 hours or 4 hours, or really can be about like 7.5671 hours, or it can be any number in between 0 and 24, right? And 0 and 24 will be the extreme cases, but hour or like number of hours or what else? Like measurements, guys. Like, hey, how tall are you? Or what is your weight? Then we can give these numbers that are not exactly be a discrete number. It's gonna be a decimal value, and it can be. And well, you know about the continuous. I'm trying to explain something that you already know. But what we are doing today is we're going to be working with continuous random variable. And if you make a distribution of that continuous random variable, we simply call it continuous probability distribution. Okay. One thing that I want you to know about in this continuous probability distribution is that suppose that, let me go back to my example. What is the probability that I ask someone, hey, how many hours do you study in a day? And they go, oh, I study about 7.4678457.5 hours. You see, it can be, I mean, to be exact, it's gonna be, you're gonna have infinitely many possible answers in between 0 and 24. So what we are saying is the probability of observing a particular value of a continuous random variable is going to be 0. Okay? And this has to do with the fact that we are using the area under these curves to calculate the probability, but we'll talk more about this. But just using that the second bullet point right here, that the probability of observing a single value is going to be exactly 0. What I want you to write down is that the probability of x being less than a value is going to be exactly the same as probability of it being less than or equal to a value. And this is true because since there's no area under the density curve associated with a single value, and right now it may not make so much sense without seeing a picture, but basically what we are saying is at a single point, we can't really have an area. So we're going to say, we're going to use an interval when we are doing the probability calculation in this continuous probability distribution. We will say something like, what's the probability that something is less than 450 or something is in between 450 and 530? So you will be asked to find an area or probability of an interval, and it's not going to be a probability that x is going to be exactly equal to, say, 5, because those will always just going to be 0. You'll see the different types, but I saw a homework problem that has to do with this, so I just wanted to kind of include those right here. Okay, all right, let's talk about normal distribution. So normal distribution is a continuous probability distribution for a random variable x, and this is probably the most important continuous probability distribution in statistics. So that's why we're going to spend about 2 hours spending on this topic this week. And now if you graph a normal distribution, it's going to be called normal curve. And in fact, you worked with this before spring break, before all this happened. And remember this nice bell curve where we put the mean right in the middle, and we created a couple more tick marks to the right of it and to the left of it using what? The standard deviation, right? So you do have experience working with this normal distribution before, but we're getting more into this in this lesson today and in the second lesson. All right, so make a note that the area under this curve is going to be exactly 1, or we'll say 100% later. But area under a normal curve is going to be 1. And if you take a look, this is a symmetric graph, right? So if this line right in the middle cuts our curve in exact half, to the left of the mean, we're going to have an area of half, right? 0.5. And to the right of it, we're going to have an area of another 0.5. So they add up to 100% together. But we'll talk about the symmetry idea in this lesson, okay? So a couple properties of normal distribution. So if you have a normal distribution, the mean, median, and mode are all equal, okay? So I think I try to highlight the words that you're going to fill out in your notes. So write down that mean, median, and mode are all equal. And like you also saw on that picture, the normal curve is bell-shaped and it is symmetric about the mean. So to the right side of the mean, to the left side of that mean, it's going to be exactly the same. And we will actually use this property to calculate a couple of these basic probabilities today. All right, now third important property is that the total area under the normal curve is always equal to 1. Okay, always equal to 1. Um, as normal curve approaches, it's gonna approach. I mean, as it approaches the positive infinity to the right and negative infinity to the left, it's gonna get infinitely close to the x-axis. Okay, it's gonna get really, really close to x-axis, but it will never go beyond. It's never gonna go below the x-axis and it needs to stay above the x-axis. Okay, let me read number 4. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. So let me go back to that picture. Can you see what number 4 was talking about right here? You see this, if you're looking at my mouse over here, as this is going forever to the right, it will get infinitely close and our eyes will just think it touched the x-axis already, but it will just get really, really, really close to the x-axis. But you should not have a graph that's going below it or curving up like an octopus shape. I saw a homework problem asking for, is this an normal distribution? And if the curve doesn't approach this x-axis like this is doing, then that's not normal distribution. It shouldn't go below the x-axis or it shouldn't curve up to be considered a normal curve, okay? So that was number 4. Number 5 is a little bit, now this will make more sense if you took calculus. I know in our class, one student is in calculus class, so she knows about concavity and everything, but there's something called inflection point. Let me talk about this inflection point and talk about that in our picture. So in between, now look at this notation for me, mu minus sigma. What does this mean? So one standard deviation below the mean, and mu plus sigma, that's going to be one standard deviation above the mean. So one to the right and one to the left of the mean. The graph curves downward, okay? The curve is going to look like a little frowny face. It's going to curve downward. And then the graph curves upward to the left of that point and to the right of that point. And now, where this curve changes from curving upward to curving downward, we're going to call them inflection points. And picture is going to explain so much better. So let me show you the picture, okay? So take a look, this dot right here. Notice how this curve is, I shouldn't say concave down. What should I say? This is, the curve, the graph curves downward. Okay, I'll just say this is graph is curving downward. And then outside of this point, the graph is curving upward. Okay, the graph is curving upward. So these 2 points, one standard deviation away points, these are called inflection points. Okay, not 2 standard deviations. Okay, it's going to be one standard deviation above the mean or below the mean. These are going to be called inflection points. Okay, all right. So Couple more pictures of inflection points. Now, look at the very first one on the left, picture A. The mean of this distribution looks like about in between 3 and 4. So the mean is 3.5 with standard deviation of 1.5. So from here, they're just going plus 1.5. So 3 plus 1.5, I'm sorry, 3.5 plus 1.5 should be about what? 5, and then another 1.5. So you keep on adding to the right to create the right side of this number line, and you keep on subtracting that 1.5 to the left to create the left side of the curve. But as you can see, if you do 3.5 plus 1.5, you will be at 5, right? If you do 3.5 minus 1.5, you will be at 2. So if you add 1 or subtract 1 standard deviation from the mean, you will find these inflection points where the graph changes how it curves. So in between those two, it was curving downward. Outside that region is curving upward to the right and curving upward to the left. Same thing is happening here. The mean is 3.52, but then the standard deviation is a little bit smaller. So in order for you to find the inflection points, you will add 3.5 plus 0.7. So it's not clear on this number line in the picture, but I'm using my calculator. The inflection point for this graph in the middle will be at 3.5 plus 0.7, 4.2 on the right side, and 3.5 minus 0.7, 2.8 to the left side. So, and those are just going to be one standard deviation away points. Same thing here, we can apply the same thing, but let's talk about the mean and standard deviation of normal distribution. A normal distribution can have any mean and any positive standard deviation. Now, this was asked on your first exam, and I got many of you on this one. A standard deviation will always be positive, but mean can be negative. Mean can be a negative number if you want it to be, but standard deviation will always be a positive number. So what do you do with these mean and standard deviation? Well, you put the mean right in the middle. You add a couple standard deviations to go to the right side of the number line, and you can subtract a couple standard deviations to the left to create the number line to the left. Okay. Now, the mean is located right at the line of symmetry. So you should be able to, in your head, fold your normal curve in exact half, and that line of symmetry is exactly where that mean is, okay? All right, the standard deviation describe how spread out the data is. So if the standard deviation increases, the curve will become more spread out. So take a look at these three pictures that I have for you, A, B, and C. Which one is the most spread out? Look, they're all centered around 3.5. Except for this one. Maybe I shouldn't look at the last one. These two both have a mean of 3.5, but they look different, right? As graph A has a bigger standard deviation, so it's spread out more. The number line for A, I have 0 all the way up to 7, while this one only kind of has, like, most of the data are centered around like 1 and 6. So this was, I saw this one on your homework. As sigma or standard deviation increases, the curve becomes more spread out. Okay? All right, so let's try to find the mean and standard deviation for our curve A and B right here. So number one, which curve has the greater mean? And you know where to find the mean, right? Mean is where that line of symmetry is. So A line of symmetry is at approximately 15. So mean of curve A is going to be 15. And for curve B, it looks like it's centered, or the line of symmetry is around at 12. So we would say that the mean for B is 12. So which curve has a greater mean? Curve A has the greater mean, as the line of symmetry for curve A occurs at x equals 15. And the line of symmetry of curve B occurs at x equals 12. Now, which one has the greater standard deviation? That's the second question. In other words, which graph is more spread out?
Now, guys, we're not looking at which one is taller. We're talking about which one is spread out more. As you can see, B is spread out more, right? Therefore, curve B has a greater standard deviation as curve B is more spread out than curve A. All right, now let's look at some data from New York State Education Department. The scale test scores for New York State grade 4 Common Core math exam math tests are normally distributed. The normal curve is shown below to represent this distribution. Now, this is a perfect bell curve. If you were to say where the mean is, what number would you say? I would say like right in the middle of these two numbers. So approximately 200 and, whoopsie, not 200. I got a better picture for you right here. Looks like, notice that the normal curve is symmetric about the mean. So you can estimate the mu or the mean to be about 305. So about here, that's going to be our mean. And to find the standard deviation, remember that point called inflection point, you try to find where the curve changes its behavior. Notice how in between this number and that number, the curve was curving downward, but as soon as we hit this point, this curve is curving upward. So because the inflection points are one standard deviation from the mean, you can estimate that the standard deviation is approximately 40. If I will ask you to do this on a test or a homework, I will make sure to give you a number line that shows more than just like an approximate number line. But that's how you can use the symmetry line and the inflection point to tell the mean or the standard deviation of a normal distribution curve. Okay? So let's make an interpretation, okay? So hopefully you have this picture written down or at least wrote down 305 and 40. 305 is the mean and 40 is the standard deviation. Let's use what we already know, what we learned before. The scale test score for the New York grade 4 Common Core math test are normally distributed with a mean of 305 and standard deviation of 40. So do write that in your blanks for me. So what we can do is we can use the empirical rule now, right? Remember, 68% of the data are going to be spread out in between within one standard deviation away from the mean. So how do you think I got these two numbers, 265 and 345? Let me show you, okay? What I did was, let me open a calculator, get a calculator. Take the 305, the mean, and add one standard deviation, plus 40. So 345 is right here. So 345 is one standard deviation above the mean. Guess how I got the 265? I go back to my mean of 305, and this time subtract 40. If you do that, you will get 265. So these two numbers are simply one standard deviation subtracted or added from the mean. And what we remember is that about 68% of the data are going to be spread out in between one standard deviation. So that's how I got that. Now let's look at the second one. Because remember, the empirical rule was three different numbers, 68, 95, and then 99.7. Now, how do you think I got these two numbers, 225 and 385? Well, we simply add 40 twice from to 305 to get 385, and then subtract 40 twice from 305 to go down to 225. And then the third standard deviation points, I had to subtract. And I think, didn't we find the typo, guys, right here? Because in order for us to get the far outbound, I need to add 40 3 times, right? So let's fix that right here. So do 305. Check this with me. 305 plus 40, I added it once. Another 40, I added it twice. And then I added one more time. And that's going to be 3 standard deviation above the mean. So I want the third one needs to say 425. So, oh, I just forgot to type the 5. So please type or write 425 for the last standard deviation, but I believe this number is right. So let me double check still. Let me still double check that with you, okay? So do 305 minus 40 3 times, minus 40 once, minus 40 twice, and minus 43 times. And then 185 is given right there. So this is the empirical rule that we went over before spring break, before all this happened. But just kind of wanted to review that with you here because you will be able to use this rule to solve couple probability problems, okay? Now, note that the empirical rule applies to any normal distribution, So, even in a standard normal distribution that we're going to talk about later, we can use this empirical rule. All right, so let's review this empirical rule a little more, okay? So approximately 68% of the area under the normal curve is within one standard deviation of the mean. So I got this picture broken down for you. Now, if you add 34 and 34, you will get 68. And you know how we can get that 34, right? I mean, it's going to be equal to the right and to the left. So they're exactly equal. So you can take 68 and divide by 2. That's how I got 34 on each side, okay? So the first bullet I got, the percent of the area in between mean and one standard deviation below is going to be 34%. This picture right here, right? And the area from mean to one standard deviation above that point is also going to be 34. And then they add up to 64 together, right? What's this one? The percent of the area more than one standard deviation above the mean is 16%. Now, guys, let's talk about that one. What I'm going to do is I'm going to copy this picture. Where can I copy this? I don't think I have like a number on a... Well, let me do my best. Let me try to create a new slide. And just make this really, really big. So this is what they're talking about. So the percent of the area more than one standard deviation above. So I'm going to cover up what I don't need, okay? So I don't need this part. Above the mean. I'm sorry, above one standard deviation from the mean. So what they are asking is, how much is to the right side of that? Now let me use my calculator to add these two decimals I see. 13.5 plus 2.35, that's going to be only 15.85, but you see how this section right there is only 2.35, so we should probably add this little section there too. But what we can use is this. No, whoopsie, I don't want that gone. Notice if the middle is 68, the outside region is going to be 100% minus 68, right? So outside, I have 32%. All right, let's see if I can use a pen. So from here to there, and from here to there, I have 32% together, right? So these two equal pieces add up to 32 together. That means if I want to get one of this section, I'm just going to have to divide this by 2, right? So that's how they got 16% for this area. So what I can do is I can figure out what this tiny little section is by doing 16 minus 13.5 minus 2.35. So what we got is only about 0.15% of the data are going to be above 3 standard deviation. And similarly, using the symmetry, below 3 standard deviation. And remember how we used this 3 standard deviation rule to talk about whether something is an outlier. So it's kind of the same idea that we're still using. But just kind of wanted to give you the breakdown of these numbers in this slide in order for you to, so that you can use them on your homework. But these numbers are nothing more than just dividing these 68, subtracting it from 1, and you can come up with those, right? All right, the middle section, approximately 95% of the area under the normal curve is within 2 standard deviation of the mean. I may ask you a question like this. What percent of the area under the normal curve is more than 2 standard deviations from the mean? So listen, 95% is within 2 standard deviation. So what I'm asking is how much is outside that region? And that's going to be, well, if 95 is in the middle, we're going to have 2.5 to the right and 2.5 to the left. So the answer for this question will be, adding these 2.5% and 2.5% together, we have 5% that are more than 2 standard deviations from the mean. Okay? That's what we can do. All right, last one. I don't really have a like an example or complicated calculation problem. Just that approximately 99.7% of the area under the normal curve is within 3 standard deviation of the mean, and that's it. That's it for the empirical rule. Let's move on to something called a standard normal distribution. Okay. All right. Still, this is a bell curve. So the area under this curve is going to be 1, okay? Now remember that in a normal distribution, the mean is going to be always, what number? 0. The mean is going to be 0 and standard deviation has to be 1. So a normal distribution with the mean of 0 and a standard deviation of 1 is called standard normal distribution. And here is the picture, okay? Notice 0 is right at the center. And as you go 1, 2, 3 standard deviation above the mean, we're going to go to 1, 2, 3 points. And to go to the left side, you just subtract the standard deviation of 1. So this looks like a number line, right? But this is the standard normal distribution. And we're going to use this curve for the rest of this slide to find some probabilities, okay? All right. Any x value can be transformed into a z-score. And you do know the z-score formula. You found the z-score of Groot and what was the other character? I think it was Yoda, I think, on your first exam. And just do want you to write down that z-score formula one more time for me because we will be using this pretty often in our, well, maybe the second lesson where we're going to convert any score into a standard score, okay? So the z-score is value minus mean, and then you're going to have to divide it by standard deviation, okay? So the normal standard distribution is a mean. It has a mean of 0 and standard deviation of 1. So I'm just repeating myself here. The total area under its curve is 1. So what happens if x value is exactly the same as the mean? If z-score is equal to 0, then what you know is that you are working with the x value that is exactly equal to the mean. Imagine subtracting two numbers that are exactly equal. You are going to get 0, right? So 0 divided by anything, the standard deviation will give you 0. So if your score is exactly equal to the mean, then your z-score will be 0. Remember that the total area under the standard normal curve is 1, and we're going to use this idea to find some, our very first probability. All right, so here's an example. According to a standard normal table, which I will teach you how to read in just a second, the area under the standard normal curve to the left of 1.25, to the left of 1.25. Look at the blue shaded region. What they are saying is area to the left of that, this blue shaded region, is approximately 0.8907. So that's like 89.07% of the data are in this blue region, okay? Now, without consulting a standard normal table or technology, the StatCrunch, we should be able to find the area under this curve that is to the left of, not positive, but negative 1.23. Now, but you know how to find, something very similar, okay? Now, if this blue region is 0.8907, you know the total sum under this curve is 1, right? So how would you find this white region that's not shaded? Okay? In order for you to find the right side of that 1.23, you will simply subtract that 0.8907 from 1. And then what you know is to the right side of positive 1.23, you have the area of 0.1093, right? Because everything under the curve, they add up to 1. If the left side was 89%, the right side is going to be about 11%, right? So what they were asking was, how much is to the left of negative 1.23? And what we're going to do is we're going to use the fact that this graph is, or this curve is symmetric. So using the symmetry, what we know is that the area to the left of negative 1.23 is going to be exactly the same as the area to the right of positive 1.23. So that area is also going to be 0.1095. Okay, so that's how you can use the fact that the total area under the curve is equal to 1. And the second part, I actually use the symmetry, right? So that's that. Got a couple more properties of standard normal distribution for you, about like 6 of them. So do take notes if you have blanks. The cumulative area. So when we say cumulative area, everything to the left of that point. So everything to the left of the point of negative 3.45, 3.49. Notice this number, this z-score is as far out to the left, right? This is more than 3 standard deviation below the mean. So the area is going to be approximately 0. So what we are saying is there is approximately 0% chance that we will get a number with the z-score smaller than negative 3.49. And if we see something like that, we'll call that an outlier, right? Now, the cumulative area will increase as the z-score increase. And the z-score on a standard normal curve, we will try to write it like, in between negative 3 and positive 3. As the z-score increases, you're going to have more and more area to that point, okay? The cumulative area for z equals 0, and z equals 0 is right in the middle, right? Right in the center, to the left of it, you will have 50% of the area. So that's going to be 0.5. The cumulative area is close to 1. It's going to be almost 100% for z-score close to z equals positive 3.49. So what they are saying is almost everything, almost 100% of the data are going to have a z-score less than 3.49. So it's very unlikely for you to see an observation with the z-score greater than 3.49. And if you do see one, we're just going to call it an outlier. Notice they said close to 1, close to 100%. So they're not saying exactly 100%, all of them. They're always going to be like 99.9999. You see, and then there's going to be some outliers outside, but it's very unlikely for us to have those values. So here is a picture of what we were talking about. As you can see, to the left of 0, we're going to have exactly 0.5. The same thing using the symmetry. To the right of 0, we're going to have 0.5 area. But everything under the curve, they're going to add up to 1. And as you can see, if you go above 3.49, it's almost going to be no area there, right? And same thing, if you go below negative 3.49, you're not really going to have any curve there, okay? Alrighty, couple more. Number 5, if the area of the left of a z-score is greater than 0.5, then the z-score must be positive. So remember, because z-score of 0 has 0.5 to the left of it, so if you get a z-score that's greater than 0.5, it must be to the right side of that z-score, that mean. Similarly, you can say if the area to the left of a z-score is less than 0.5, like 0.4 or 0.3, like, you know, less than 50%, then what you know is that z-score must be negative, because half is exactly in the middle of z-score, and in the middle is going to have a z-score of a 0. Okay? All right. I think this will be the last one. If the area to the left of z-score is equal to 0.5, what does that mean? So you have exactly half of the area to the left of this point. This is the midpoint. This is the median, right? And in fact, in a normal distribution, mean is equal to the median, right? So z-score must equal 0. Okay? So here's an example, just something that I wanted to kind of add. If you have the area under the normal curve in between negative 1.5 and z equals 0, so it would be great to have a picture. Let me see if I can draw a picture of this. I'll go ahead and copy this. I'll do my best to draw this picture with my mouse. Okay. Is there a pencil tool? I mean, guys, I have an iPad and an Apple Pen. I should be able to. Is there like a sketch pad or drawing pad here? I want to draw so bad. Nope. Maybe not. Oh, I want to draw so bad here. But I don't know if there's like a pencil tool. You know what? Okay, I'm just gonna have to do this without a picture. Sorry. All right. So let's just explain this. Let's talk about this. Maybe you can draw a picture on your paper, right? Oh no, guys, hold on. I know. I'm spending time. But look, I checked out something from the library the other day. I want to show you. I'm going to my temporary office right now. My dining room. All right, you'll see something. Ow! Hello. I can draw here. Okay, so what I'm gonna do is I'm gonna draw this on my paper. Okay, so if the area under the standard normal curve in between, let me draw a standard normal curve first. A curve. What's in the middle? 0, right? And then we have 1, 2, and 3, and -1, -2, and -3. What are they saying? It makes so much sense to draw a picture here. From in between -1.5, so about right here, all the way to 0, what they are saying is, if this purple section that I just shaded has an area of, this has 0.4332. What are they asking? Then the area under the standard normal curve between 0 and, let me grab another colored pen right here, from 0 and positive 1.5. From here to there, oh, they're just simply saying this to us, is going to be 0.4332. I mean, in a picture, you're gonna go, duh, right? It's very obvious because it is symmetric, and -1.5 and positive 1.5 are equidistant from the center. So of course it's going to be the same, and that's what I kind of wanted to draw and show you. But now I know I got this cool tool that I can hook up to. Anytime I want to draw, I'll do this. This was pretty cool. Alrighty. Let me close this guy. All right, and I'm gonna go back up here and continue talking about the rest. I don't have too many things left. All right. Now, this time, I want you to go and download the standard normal table from Canvas. We're going to use a table now to find about 5 different examples, to do about 5 different examples. So go download the standard normal table, and we're gonna use that on some of these problems. So you go to Canvas, you go to Modules. Now download this one, Standard Normal Table. It should be 2-page document. How can I, I'm going to click on this link and I'll just open it on my computer. What this table does is if you know the area, it's going to tell you how much, if you know the z-score, it's going to tell you how much area it has to the left of that point. So you know something, z-score of 0. Z-score of 0 is right in the middle, right? So if you're right at the middle, how much area should you have to the left of it? Exactly 0.5, right? So let me find the z-score of 0.5. These are all negative z-scores. But right here, z-score of, well, it's got negative 0.0, which is the same thing. Z-score of 0, what they are saying is that it has an area of exactly 0.5. And what they do is these are going to be the 10th digit of the z-score, and this side you're going to be able to find the 100th digit of the z-score. But this is a table that we're going to use. We're going to use this and find some probabilities, okay? So have this on your computer and you should be able to use this table, or maybe my stat lab will give you their own table when you're doing the table method on this homework. Alrighty, let's go back and look at a couple more examples. Now, I want you to find the cumulative area that corresponds to a z-score of 1.15. Let me do that with you, okay? 1.15. So what you need to do is find on the left column, find 1.1, okay? 1.1, okay? And then you go to the row that says, or the column that says 0.05. So together they make a 1.15, right? So if you look at their intersection, you're going to be able to find that the area is going to be 0.8749. Now just reading this table may be a new thing, but maybe we'll make up another one. I'm going to go to this table right here. I'm going to go to this table, not that one, this table right here. And what I can do is, maybe I should be able to write on this document. Let's do that. What if I ask you to find the area to the left of z equals negative 2.61. Let's try that one together. You're gonna have to find negative 2.6 on the first column, okay? So let's find that. Where is negative 2.6? Negative 2.6 is right here, right? So let's see if I can draw here. Negative 2.6. So these are going to be all negative 2.6. This first one is going to be negative 2.60. This will be negative 2.61. And in fact, you notice how the intersection of this row and this column right there, that's how you read the z-score, the area for z-score of negative 2.61. So the answer is going to be 0.0045. Let's try another one. Okay, let's try another one. How about if I ask you to find the area to the left of, let's say, negative 3.38. Okay, what about if it's negative 3.38? Then what you're going to have to do is go find negative 3.3, which is right here. Negative 3.3s are all over here. And then you're going to have to find the 100th digit is 8. So go all the way to 0.008 and their intersection right there, that's going to be, so the answer is going to be approximately 0.0004. So that's how you read it if they're asking you for the area to the left of that point. Let's try a couple positive cases too. What if they ask you to find the area to the left of 1.75? 1.75. Let's try that. Find 1.7 first. 1.7s are all over here, right? But I need my 100th digit to be 5. So all the way up here, I see these are going to be the columns for 0.05. So right here where they intersect, what is going to be the answer for this? The final answer will be 0.9599. That's how you read it. Okay, that's how you read it. Okay. So this table, the first one, number 1, was talking about finding the cumulative area, the area to the left of it. So that's what we did. The area to the left of z-score of 1.15 is this number right here, 0.8749. All right. How about find the cumulative area that corresponds to the z-score of negative 0.24? Well, you just have to find the negative 0.2 on the left column and find 0.04 and find their intersection, and the answer is going to be 0.4052. I got a couple homework problems for you to try on my stat lab. So if you're having issue reading this standard normal table, just email me. We will do a couple together over Zoom. Okay? All right. How about this one? If you try to do this one, well, I'm already showing you the answer, but let's try this one together. They want the area under the curve to the left of z-score, negative 0.99. So I need my table, negative 0.99. So the negatives are all going to be on the first page. So I'm going to go to the negative side, negative 0.99. So I see it. Negative 0.9s are all over here, right? Negative 0.9s are all over here. And I need to find which row, which column are doing the 100th digit of 9. And that's going to be all the way at the end. So the answer is going to be right here. Sorry if you can't see. 0.1611. Okay, so the answer is going to be 0.1611. Why is this slightly different? Oh, no. They got the right area here. I just wrote the wrong number. So let's type the answer here for them, okay? So the answer should be from the standard normal table, the area is equal to 0.1611. That's it. So I'm going to go ahead and get rid of this wrong answer by cropping it out. And that's perfect. I'm glad we checked this together. All right, let's do number 4, where we have, oh, look at this one. Area under the curve to the right of z equals 1.06. So what we are going to have to do is, because a standard normal table will only give you the area to the left of it, but what you know is left plus right will always be equal to 1, right? So still use the table and find the z-score, the area corresponding to 1.06. Let's do that. Where is 1.06? Here it is. All the 1 points are right here. 1.0s are all over here on this row. And they wanted what? 1.06, right? So I'm looking at 0.06 columns. I know that the area to the left of that point is going to be 0.8554. But that's not our final answer though. What do you have to do to that? You have to do, well, knowing that the left side is 0.8554, to find the area to the right of it, guess what we do? You have to just subtract 1 minus 0.8554. That's why the answer is going to be 0.1446. Okay, so if they ask you to find the area to the right side, then you're going to have to subtract. Okay, and it's because just the table, it's going to always give you the area to the left of it. They're going to give you the cumulative area to that point. So if you need to find the area to the right, you need to subtract the left area from 1, okay? Now, the most tricky one that I say for number 5, oh, this one, you want to find the area in between two numbers. Now this one is going to be a little bit tricky. So what we're going to have to do is find the area to the left of both negative 1.5 and 1.25. Let's find those two numbers first. So the numbers that I want is negative 1.5. I'm writing this down. Negative 1.5 and positive 1.25. So find those two areas using our table. So let me start with the negative one. Negative 1.5. All right, I'm going to go ahead and get rid of some of these highlights that I used. Where is negative 1.5? It's exactly right here. So write this number down. The number that we have is 0.0668. So the area to the left of negative 1.5 is 0.0668. Now let's find the area to the left of 1.25. That was the other number they gave you, right? So go to 1.25. Where are my 1.2s? These are all my 1.2s, but I'm specifically looking for 1.25. So where these two intersect. And that corresponding area is going to be 0.8944. Okay, 0.8944. So the first thing that you do is you write down these two areas, and I'm about to explain to you what I'm doing with these two numbers, okay? So what we got going on is this so far. So here is the curve, here is the 0, and 1.25. Say that that's about right there, okay? What we know is to the left of 1.25, I'll use up all this, ink today. What I'm highlighting or what I'm shading, this region is going to have 0.8944 area, right? Now, what we also just found out is that negative 1.5, I'm just going to put it right here, to the left of negative 1.5, what I'm shading on top of that, that's going to be 0.0668, okay? What they want in this problem was from here to there only, from here to there only. So they want the in-between. So what we're going to do is we're going to do this gray area minus this purple area. So the math that you're going to do is just subtraction, 0.8944 minus 0.0668, and the area in between those two values will be 0.8276. So that's what you're going to have to do. If you're finding the area in between two z-scores, you're going to have to find them both, and you will have to subtract. Okay, and the good news is the area is going to be always positive, so you will never get a negative answer when you're doing these probability problems. So that's why the area in between is going to be 0.8276. So approximately 82.76% of the area are in between these two given z-scores. Okay, so it's going to get much easier if you start using StatCrunch, but I do want you to practice using these normal table because it's not that bad. You just have to read the numbers and do some basic operation, either subtract or just keep it as is. But now you're really ready to start on your My Stat Lab homework, week 8 homework part 1. So I want you to try that, and I'm going to wait for your email. If you're stuck on a problem, we can go over those together. But it's been about 59 minutes on this video. So, well, thank you for watching for the last hour. I will be back with the second lesson and the third lesson, and you will see them shortly, okay? Thank you.